One of the problems that we want to solve this week is as follows. We're given an integer which consists of the digit 1 repeated n times in a row, like this. And what we're being asked to show is that if this integer is a prime number, then the number of digits n must also be a prime number. And so the proof will start out like this. Let's think about the number x and the digits 1 repeated n times in a row, which, by the way, we know we could express as the sum of these integer powers of n, because the first digit is a 1 with n minus 1 zeros following, so that's 10 to the n minus 1. And the second digit is a 1 with n minus 2 zeros following, so that's 10 to the n minus 2, and so on, adding them up all the way down to the last digit of 1. Thinking about it, we realize that n has to be bigger than 1, because if we had one digit, x would be 1, but that's not a prime. And we're being given that x is a prime number, so that means that the number of digits n needs to be some number n bigger than or equal to 2. Notice that if n is 2, we would have the number 11. And 11 is a prime, and the number of digits 2 is also a prime. So that agrees with the theorem that we're trying to prove. And what we want to know is that always true? If I have a prime, does the number of digits n have to be prime as well? What we're going to do is we're going to prove this by contradiction. So can I remind you of what a proof by contradiction looks like? So if we're going to prove the proposition, if A is true, then B is true, then the proof by contradiction goes like this. We'll assume that A is true, but that B is not true, and then we'll follow a sequence of correct mathematical arguments, and we'll end up deriving a statement which is impossible. So the conclusion will be that if A is true, B must be true. In our case, the statements A and B are like this. So statement A, x is prime, and statement B, n is prime. So we're trying to prove that if x is prime, then n is prime. And so the proof by contradiction will work like this. We'll assume that x is prime, but we will assume that n is not prime. And we'll go through a sequence of mathematical steps, and we'll derive something that is not possible to be true. Now, when you do a proof by contradiction, you can't always predict what impossible statement will result. But one possibility that might happen is that we'll find out that if we assume that x is prime but n is not prime, maybe we'll find out that the result is that x is not prime, but that x can be factored. And that indeed would be a contradiction. So if I'm thinking like that, then I think I want to try to put x into a mathematical form that could be easy to factor, because I'm thinking about maybe if I assume n is not prime, maybe what will happen is that we'll be able to factor x. So I'm going to try to put x in a form that could be factored. So that's what I'm thinking about when I do this next step. Now whenever I see a sum of integer powers like this, it's very helpful to think of this algebraic identity here. So let's recall that for any number a and for any positive integer n, a raised to the n minus 1 has a root a equal 1, so that a minus 1 is a factor of this polynomial, and the other factor consists of a sum of all of the powers of a which are less than n. And this form is just like this form that we see up here, where a is 10. And so if I were to take this sum and multiply it by a minus 1, it would sort of take that whole sum and collapse it down into this difference here, which is easy to factor, which is kind of what I'm trying to do. I'm trying to factor x in some way. Now let's just for a moment refresh why this identity is true, just in case you forgot. So I can verify that this is true by using the distributive law and multiply this all out, and I'll show that I do get a to the n minus 1, like this. Now the distributive law says that if I want to multiply a minus 1 by this quantity, I first multiply a times this quantity, like this. There we go. This will give me a to the n plus a to the n minus 1, and so on all the way down to a. And then I multiply this sum by minus 1. And that gives me all of these negative results. Negative a to the n minus 1, negative a to the n minus 2, and so on down until negative 1. And then I notice that when I sum up all of these quantities, most of them cancel out because the positive terms cancel with the negative terms, like this. And so what remains when we sum up all of these terms is that the only terms that remain are the very first positive term and the very last negative term, like that. So that a times this sum plus negative 1 times this sum adds up to a to the n minus 1. So what I'm thinking about here is to try this trick here, like this. So with a equaling 10 in this sum, a minus 1 is 9, and that's why I multiplied this sum by 9, so that I can collapse this sum down into 10 to the n minus 1 over here, which can be written down in this factored form like that. And now I can solve for x by dividing both sides by 9. Now it's true that up to this point, in order to accomplish this, I did not need any of this, because it's easy to see that 9 times x is n 9s in a row, and that if I add 1 to this, it'll give me a 1 with n zeros in a row after it. And so we know that 10 to the n minus 1 is 999 n times. But I like to point out this algebraic identity because of the fact that I'm attempting to factor x, and so this identity is going to come up again in a minute, and it's going to help me factor x. So what we have so far is we've expressed the n ones in a row in terms of 10 to the n minus 1 over 9, and we've been given that x is a prime, and so that means that x is 10 to the n minus 1 over 9 for some value of n greater than or equal to 2, and we're trying to prove that n must be prime. And so we're going to try to prove this by contradiction. So we're going to assume that n is not prime and then see what happens. So we're going to assume that n is not prime. Now, since n must be greater than or equal to 2, for n not to be prime means that n must be the product of two numbers n sub 1 and n sub 2, where both of them are greater than 1. Now let's see what happens in that case. So let's substitute the n is equal to n sub 1 times n sub 2 into this expression, and let's see what happens. Then we get that x is equal to 10 raised to the power n sub 1 times n sub 2 minus 1 over 9. But this can be rearranged by the rules for exponents. We can write 10 to the n sub 1 times n sub 2 in this way. It's 10 to the n sub 1 raised to the n sub 2. And this could be, call it a, and now we're back to this format where you have some number a raised to a power minus 1 over 9. And that brings us back to this algebraic identity here, because we have a to a power minus 1 in the numerator, and that can be factored like this. So if this numerator in x can be factored, then it's possible that x can be factored in a non-trivial way, but then that would mean that x is not prime, and that would be our contradiction. So let's proceed and follow this formula and find out what happens. So our next step looks like this. And so I've just followed the formula, and I've taken my power of a minus 1, and I've factored it in this way, where my n is n sub 2 in this case. And I've factored out a minus 1, and then what's left is the factor consisting of the sum of all the powers of a, which are less than n sub 2. And so since a is 10 raised to the n sub 1, I'll substitute that back in. So we'll see how that looks. So how does that look? That looks like this. And so a minus 1 is replaced with 10 raised to the n sub 1 minus 1. The 9 in the denominator, I moved it over here underneath this term. And then the rest of this is the sum of powers of n that looks like this, because 1 is 1, and a is 10 to the n sub 1. A is 10 to the n sub 1. a squared, how would I square 10 to the n sub 1? That's just 10 raised to the 2n sub 1, and so on, proceeding to the left, where my last term, a raised to the n sub 2 minus 1, is 10 raised to this product, n sub 1 times n sub 2 minus 1. So, by assuming that n is a composite, it looks like I've managed to factor x in a non-trivial way, which would be my contradiction because x is supposed to be prime, so I'm not supposed to be able to factor x, but this is a non-trivial factorization because look, this number here is just the digit 1 repeated n1 times, but n sub 1 was assumed to be greater than 1. So I have more than one digit here, so that this number is greater than 1. In fact, it's at least as big as 11. And what about this term here? It's also bigger than 1. If I think about it for a minute, because this term here, count the number of terms in this sum. 1, 2, 3, la la la, all the way up to n sub 2 minus 1. So there are n sub 2 minus 1 terms here, and this 1, which gives me n sub 2 terms. So this sum contains n sub 2 positive terms. But remember, n sub 2 was also assumed to be greater than 1, which means that I have more than one positive term in this sum, including the term 1, which means that this number here is also greater than 1. So I've factored x into a product of two terms, each of which is greater than 1. So we've managed to factor x in a non-trivial way. So this means that x is a composite number, but this is a contradiction because we were given that x is a prime. Therefore, it was wrong for us to assume that n is a composite number. So since it was wrong to assume that n is a composite number, and because n must be greater than or equal to 2, it follows that n is prime whenever this number is a prime. And the problem is solved. I conclude with some further remarks about this problem. These numbers we have been dealing with, there's a name for them. These are called repunits. And repunit stands for repeated unit. And often the symbol r sub n is used to indicate the repeated unit n times. And this word was coined by Albert H. Beiler in his book, Recreations in the Theory of Numbers. And as an interesting note, a repunit can be done in any base, and in any base B, the unit 1 repeated n times in a row in base B can be calculated in base 10 by using the formula b raised to the n minus 1 over b minus 1. In our case, when b was 10, recall that x was 10 to the n minus 1 over 9. Rep units in base 2 are called Mersenne numbers, and prime rep units in base 2 are called Mersenne primes. The first few rep units in base 10 look like this. R sub 1 is 1, R sub 2 is 11, R sub 3 is 111, and so on. And we observe that this string of numbers is agreeing with the theorem we just proved. For example, 11 is a prime number, and its number of digits, too, is also prime. The theorem does not go the other way, however. Just because the number of digits is prime, like 3 or 5, does not mean that the corresponding rep unit is a prime. For example, R sub 3 is 111, which factors like this, and so it's not prime. And R sub 5 is 11,111, which factors like this, and so it's not prime either. So just because the number of digits is prime doesn't mean the rep unit is prime, but the theorem only goes one way. If the rep unit is prime, we know that the number of digits must be prime. So you might ask, well, how can you determine if a rep unit is prime? Actually, this is a non-trivial problem, and the search for prime rep units is ongoing. I can show you the very first 5 prime rep units. They are R sub 2, R sub 19, R sub 23, R sub 317, and R sub 1031. Notice that in each case the number of digits is indeed prime. I actually found it quite easy to prove that these 3 numbers are prime by using my personal computer and just using the ifactor command in Maple. But the ifactor command was very, very slow for any numbers once I got more than 100 digits. So trying to prove these are prime, especially as they get larger, is a non-trivial problem. And we don't know for certain any more prime rep units at the moment. But according to the online Encyclopedia of Integer Sequences, as of August 2014, it is believed but not proved that R sub n is prime for the following 4 values of n. Okay. And that leads us to the next question. Does this list of rep units go on and on forever, or does it stop? And we also don't know the answer to that question either. According to Wikipedia, which referenced this page by Chris K. Caldwell from the University of Tennessee at Martin, it is conjectured that there are infinitely many prime rep units. But this remains an open question.